Welcome to iLecture Online. Here we're going to try, at least we're going to attempt to find the arc length of the sine function. Here it is, f of x equals sine of x, and we want to find the length of that curve from x equals 0 to x equals pi. And you would look at that and go, that looks really straightforward, piece of cake, no problem at all, but you'll find that it's a whole lot more difficult than it appears. And that's what they don't tell you when we deal with arc length, that most of the examples they give you in the book and most of the exercises are worked out just so that you're able to do that integral. The difficult part always is that quite often you end up in an integral here that you can't integrate. And let me illustrate why that is so. So our function f of x equals sine of x. So when we take the derivative, f prime of x, that's equal to the cosine of x. And f prime of x squared, well, that's equal to the cosine squared of x. So far, so good, really easy. You plug that into your integral right here, so we have the arc length is equal to the integral from 0 to pi of the square root of 1 plus the cosine square of x dx. And I say, okay, I can figure this out, can't I? But it turns out, no, that's an integral that we cannot yet do using the typical techniques that we use in our calculus course. Doesn't matter what you try, you can't do it. I tried. Cannot be done, not at least with the typical techniques that we have. So, how do we solve this? Well, we can use what we call Simpson's rule. And Simpson's rule is as follows. So Simpson's rule. If we have an integral of, let's say, the function g of x dx, what we can do is we can snip it up into many little pieces in such a way that the integral can be approximated by, when we integrate from a to b, for example, when we take the difference, we take b minus a divided by 3 times the number of snippets that we take, times 1 times g evaluated at the first point, plus, I don't have a lot of room here, don't I? Plus 4 times g evaluated at the second point, we call that x of 1, plus 2g of x at the third point, plus 4g of x at the fourth point, and plus 1 time g of x at the fifth point in the example where n equals 4. We take 4 snippets, and of course there's the end points and 3 points in the middle, so we have to evaluate this at 5 different points. So this is how we do that. So in this case, as an example, we have n equals 4. So applying that to our example right here, we then say that, well, g of x, in this case, g of x is equal to the square root of 1 plus the cosine square of x. So that means we need a table of values. We're going to have a number of x's, and we're going to have the square root of 1 plus the cosine square of x. And of course, here we have x of 0, x of 1, x of 2, x of 3, and x of 4. And we integrate from 0 to pi. So our first one will be 0, our last one will be pi. And then we have pi over 4, we have pi over 2, and we have 3 pi over 4, like that. So that will do it. Now we need to find the corresponding values for the square root of 1 plus the cosine square of x, which is, of course, our function that we're trying to integrate. So therefore, I need a calculator. Starting with 0, of course, that's easy. When the cosine of 0 is 1, 1 plus 1 is 2, we get the square root of 2. That means over here, when we have pi, that's negative 1 squared is positive 1, so we'll also get the square root of 2. How about pi over 4? That's 45 degrees. So that's the square root of 2 over 2. So in this case, we have the square root of 1 plus the square root of 2 over 2 squared, which is equal to 2 over 4, 1/2, plus 1, that's the square root of 3/2. When pi is 1/2, so we have, that would be 0 plus 1, we have just, well, that's right, that's cosine of 90 degrees is 0, plus 1, so we have the square root of 1. Okay, then here, for 3/4, we'll have the square root of 3 over 2, and then we have 2. There we go. Those are the 5 values. Now we plug that into our Simpson's rule here. So this would be equal to b minus a. So from 0 to pi, that would be pi divided by 3 times 4 times 1 time the value for the first one, which is square root of 2, plus 4 times the square root of 3 over 2, plus 2 times 1, plus 4 times the square root of 3 over 2, and, oh, I need to include that. Didn't go far enough. There we go. Okay, and plus 1 time the endpoint, which is the square root of 2, and a bracket. All right, that should approximate the length of the sine curve from 0 to pi. All right, so this is equal to pi divided by 12 times. And the square root of 2, well, 2 times the square, that's 1.414 plus. So we have plus 1.5, take the square root, times 4. Oh, I didn't get my intermediate value. Let me do this again. So take the square root of 2 plus intermediate value. 1.5, take the square root, times 4. I think it says 4.899 equals. All right, that's good. Plus 2 equals. Plus the same thing again. Plus we have 1.5, take the square root, times 4. Yeah, I really didn't need to calculate it. It's 4.899, you're right. But I need it in my calculator so I can add it up. Equals. And then plus the square root of 2. So plus 1.414. So now we end up with pi divided by 12 times what I have here is 14.626, which is, so times pi divided by 12, and then I end up with 3.829. So the arc length of the sine function from 0 to pi is approximately, and of course, let's see, I should go approximately, right? Because it's not exact, but pretty close. Actually, when you do find the real value, it is very close to the value that we found. And so it's a pretty good method, even with n equals 4. Of course, when you have n equals 10 or 20 or 100, you're going to get a much better value, but that would take you a very long time doing it by hand in a calculator. But that's how it's done. Notice we end up with an integral we cannot integrate because it's, it's not by traditional methods at least.
That was a negative sign you can integrate it.
Yes, if it was a negative sign, you turn into a sine square, and then of course that would be easy. But unfortunately, it's not a negative sign. And any identity you try, I tried a number of identities, it's just, yeah, it's not, by traditional methods, you're not going to find the integral.
So what's the actual answer?
It's really close to this. It's 3.8, really, really close. I don't know the exact answer, but I know we're close. I could look it up. All right, that's how you do that one.